This video is Team Thundercat's video submission for Lab 4 IoT Cloud. This video covers the following topics, including Part 1 and the extra credit section Part 2. So to start with Part 1, we'll talk about getting acclimated with Jupyter Notebook via the notebook practice file. So this task required us to complete 7 to-do items, the first one being to create an empty array with the dimensions of 15 by 29, which we did so here. And then we converted the same array into a ones array using operations. Then we created another array, 8 by 9, with values of 5 to 11, which we accomplished using operations again, as seen here. For the fourth task, we had to create a data frame containing demographics of me and 2 friends. So here you can see our data frame containing demographics of me, Madhu, and my 2 friends, Rachel and Ross, which I accomplished through a dictionary. For the last 3 items, the first task was to add a new row to the data frame containing information of another friend, Monica. So I did so via this dictionary, which I appended to our data frame, and we can see the results here. Then the next task was to grab my information from this data frame. So I accomplished it using .lock. And the final task was to grab the name of my second friend using the .iat function, which I did so here, and we can see the results are accurate. Next, we acquire and parse the data set. So we went to the provided Google Drive for this lab, and we downloaded these 3 files. We followed Sumo documentation to convert the XML file into a CSV, and then uploaded the CSV into Box. This link has been provided in our report. Now we're going to dive into machine learning on pollutions from transportation. So let's take a look at the Notebook Learning 2 file. And here in the first half, we're importing libraries, we're importing the data set. This CSV file is actually the CSV that we generated from that XML. And here we're doing a lot of data cleaning and writing down our observations, as well as some code to drop unneeded columns, etc. And in the second half, we create and train a model with both small and large data. So in this file, we'll be talking about training our model with small data. Here we have code to split our data into training, validation, and test sets. We don't normalize the input data because we want an unnormalized test MSE at the end. And also I organize and classify the features, but we did try to constrain our features during our multiple tests to try and get the desired MSE that we needed for this lab. Here I also create a feature layer, and scroll down here, you can see our hyperparameters for this model. So we have a learning rate of 0.03, 1,000 epochs, batch size of 128. We have 3 hidden layers with ReLU activation, and each have different numbers of units. And our output layer has a linear activation. So here are our training results, and here you can see our test data evaluation, and we have an unnormalized test MSE of 56, which is below our target MSE of under 100, which is great. And here we use TensorBoard to see our logs, and as you can see here, we can see our epoch loss and our epoch MSE. The train results are in pink, and the green represents validation. And the following visualizations show how our predicted and targeted values match up, as well as our error count histogram. And as you can see, a lot of our error counts are located mostly around 0, which means that our trained model is pretty accurate. And here you can see a table of our actual versus predicted values. And this file, Notebook Learning 2 with large data, is essentially a duplicate of the previous file that we just discussed, except we have some differences here in how we're splitting the data because we don't want data going into backup DF. And otherwise, the main differences here are in our parameters. So here we have a lower learning rate, we have 50 epochs, and we have 10,000 for our batch size. But otherwise, we have similar information here, 3 hidden layers again with ReLU activation, etc. And as you can see here with our results, we have an unnormalized test MSE of 151, which is great because it's below our target of 200. And then here you can also see again how our targeted values and predicted values match up, as well as our error count histogram. And again, the error counts are mostly located around they're mostly located around 0. So our model must be pretty accurate. And again, you can see our table of actual and predicted values and how they.
In this portion of the lab, we use the TensorFlow playground to analyze different sets of data. Here, we use the ReLU, sigmoid, linear, and hyperbolic tangent functions on the circle dataset. After observing the results, we note that the ReLU and hyperbolic tangent functions give us the best results. Both the sigmoid and the linear functions don't perform very well in this exercise, and after doing some research, we found that this could be due to the vanishing gradient problem. If we take a look at the sigmoid function, we see that the input space is compressed between 0 and 1, so therefore the weights and biases may not be updated effectively, and that leads to a larger loss rate. Next, we go through various learning rates for each of the different functions, and as we go through the results, we can see that they are very sporadic. If we look at the hyperbolic tangent function specifically, when we use a learning rate of 10, the test loss and training loss are very high. And this is due to the fact that the gradient descent may not be converging because we're using such a large learning rate. Additionally, when we analyze the node weights, we see that they can be negative and change over time. In this situation, you can see where the weight goes from 0.46 to 0.60 around 500 epochs later. Next, we take a look at L2 regularization using the ReLU function. And we actually found that in this instance, we get slightly better results without regularization as the loss rates tend to stabilize faster and they're also a bit lower. Next, we analyze the spiral dataset. Although regularization did not improve our results, we found that there was significant improvement when we added the x1 squared and x2 squared features. Making the batch size smaller just led to increased volatility. Using the hyperbolic tangent function did lead to better results. We found that the additional features were needed to match the more spherical coordinates of this dataset. After using different combinations of hidden layers and nodes, we found that we got our best result by using only one hidden layer with 6 neurons, and that led to an extremely low loss rate of 0.009 for both test and training. However, this does lead to the risk of overfitting for the dataset. Finally, we tried various methods on the additional regression and classification problems. We found that the effectiveness of regularization varied by dataset. For instance, most functions performed well without regularization on the regression dataset with no noise. However, adding L2 regularization gave us good results without having to train for a large number of epochs. In this last example, we only needed to train for 13 epochs using the hyperbolic tangent function to achieve a great result, even though we had introduced a small amount of noise to the dataset.
Messages from 12 simulated devices to our AWS MQTT test client. So we are subscribing to the topic test info. You can see here we're in an EC2 instance which holds our certificates, and we are going to run this script. And as you can see, we have now sent those messages. So the script is working as expected, and the payload is message CS437 lab4 AWS test in JSON format.